This question is similar or related to two other questions that I answered in a separate video to which I'll link here. The question says, if 42 kilojoules of heat is added to a 32 gram sample of liquid methane that's starting at negative 170, what's the final temperature and state of the methane when you're all done? As I've stated elsewhere, and once again I'll link to it here, whenever you're going up one of these slopes on a heat curve, you use this equation, which happens to be equation 5.22 from our text. So that tells us how much heat is required to go up a slope. Whenever you're traversing one of these plateaus, which represents a phase change, that is the change from a solid to a liquid or a liquid to a gas, you use this equation, the plateau equation. For my students who are taking this from me, I'll actually give you these two equations. I will not write the word slope or plateau next to them, however, so make sure that you know how to use them. So here's the deal. What I need to do is determine how much heat is going to be required to take my 32 grams of methane and warm it up from negative 170 to negative 161.5. That is the actual temperature where methane starts to evaporate or turn from a liquid into a gas at 1 atmosphere pressure. So that is the temperature difference. I'm going up a slope, so I'm going to use my slope equation. All right, now Q equals the mass I've been given, which is 32 grams, multiplied by the specific heat of methane. The specific heat of liquid methane is given to us in the problem. It's 3.48 joules per gram Kelvin. Then I'm going to have to multiply that by delta T, which is the difference in temperature. Negative 161.5 minus a negative 170. And if you minus a minus, it's like plussing. And that's in degrees Celsius, which once again admittedly doesn't cancel out degrees Kelvin. However, keep in mind, the only difference between Celsius and Kelvin is 273.15, which means that if I took this temperature, converted to Kelvin, I would add 273.15. Took this temperature, added to Kelvin, I would get also add 273.15. The difference between the two would be exactly the same. So I can cancel out my kelvins, I can cancel out my grams, and I end up throwing that into my calculator. The final answer ends up being 947 joules, which, if you're okay with me jumping the gun here, is the same thing as 947 kilojoules. So this distance, A, is going to consume 0.947 kilojoules. That's the cost. Now the next thing I need to determine is how much energy is going to be consumed going across plateau B. So this is the cost of A, the cost of B. B is a plateau, so I'm going to use a plateau equation. Q equals mass. The mass I've been given is 32 grams, multiplied by the molecular weight, 1 mole of methane gas, and it gives me the well, maybe it doesn't give me the formula. The formula is CH4. That is 16 grams, multiplied by the enthalpy of phase change. That is going from a liquid to a gas for methane. The delta H, that enthalpy of phase change for that particular phase change, liquid to gas, has been given to me in the problem as 8.2 kilojoules per mole. So now all I have to do is cancel out my units, and I'm left with a certain number of kilojoules. I throw that in my calculator. The answer that I end up getting is 16.4 kilojoules. So that means that going across B costs me 16.4 kilojoules. So I've spent 0.947 kilojoules going up here, and then I've spent 16.4 kilojoules going across here. Now I'm right here at that point. Now what I need to determine is how much energy I have left. It tells me in the original problem that I cranked in 42 kilojoules of heat. So how much do I have left? I've spent 0.947 and 16.4. So if I take 42 and I subtract from it 16.4 and 0.947, how much heat is left in kilojoules? The answer is 24.65 kilojoules. And hopefully you're okay with this. I'm going to make the conversion to 24,650 joules. The reason is because we're now going up a slope. I need to determine what the final temperature is. So, if you're okay with this, I'm going to erase these two. I'm now going to use this slope equation. But delta T is the thing that I'm trying to figure out. So, I'm going to use this equation. I already know what Q is. Q is that. If you algebraically rearrange it, you can figure out that delta T is going to be equal to Q divided by M times specific heat. So Q is once again 24,650 joules, and I'm going to divide that by the mass I've been given, which is 32 grams, multiplied by the specific heat of now gaseous methane, which has been given to me in the problem as a 2.22 joules per gram Kelvin. There we go. My grams cancel each other out. My joules cancel each other out. My Kelvin is in the denominator of the denominator, which means it's in the numerator. And when I crank that out in my calculator, I get 347 kelvins. So I'm basically increasing the temperature 347 kelvins. I'm starting at a temperature negative 161.5. So if I'm starting at negative 161.5 degrees Celsius and I add 347 to it, I should get to a final temperature of 185 degrees Celsius. So that is the answer. That's the final temperature, and it asks you what the final state is, and the final state is a gas.